Most information we get from distant objects in the universe is in the form of light. For this reason, a good understanding of the nature of light, how it is produced, and how it interacts with matter is fundamental to the study of celestial objects. As familiar as light might seem to you, it has a mysterious nature that combines properties of waves and properties of particles at the same time. Depending on the physical conditions, scientists might recur to the particle or to the wave properties of light to interpret the outcomes from experiments. Let's look at the wave nature of light. A wave is a perturbation that propagates and transports energy with it. Ripples on the surface of water are a good example, with a circular pattern propagating outwards from the point where the water is initially perturbed. In this case, the perturbation consists of vertical oscillations of mass of water and the wave transfer energy of motion known as kinetic energy. Similarly, an electromagnetic wave is a perturbation, but the perturbed entities are the electric and magnetic fields, and the energy they transport is called radiant energy. To better understand what an electromagnetic wave is, we need to look at the interaction between electric charges. When two electric charges are placed in proximity, they exert an electric force on each other. This force acts even if the charges are not in physical contact, because the interaction is mediated by an electric field created in the space around each charge. A particle with positive electric charge creates an electric field that we can visualize as radial lines pointing away from the charge. When an external charge is put inside the electric field, the interaction of the field and the second charge results in a push or force on the charge. Positive charges are pushed in the direction of the field, while negative charges are pushed in the direction opposing the field. A notable event happens when an electric charge moves. If the position of a charge changes, its field lines must readjust to keep its radial alignment with the charge, and a perturbation of the field is created and travels as a pulse through space. As a consequence of the laws of electromagnetism, oscillating electric fields produce a magnetic field similar to the one that exists around a bar magnet. Thus, the electric wave is always accompanied with a perpendicular magnetic wave that mirrors the electric oscillations. These coupled and varying electric and magnetic fields form an electromagnetic wave. In this animation, an electromagnetic wave traveling through space is observed. The electric field is shown in red and magnetic field in blue. In contrast to the waves of water that need the presence of the liquid to travel, electromagnetic waves do not need a material media to propagate, and that explains how light from distant stars can reach our eyes traveling through large distances of almost empty space. Since light is a wave, we can characterize it using parameters common to all waves. The distance between two crests or troughs is called the wavelength. Since we are measuring distance, wavelength is usually given in units of meters. If now we look at a wave passing at a fixed position, the number of waves passing that location each second is the frequency. Frequency is given in units of cycles per second, also called hertz. Since the wavelength is the length of each wave cycle, and the frequency is the number of cycles that the wave travels each second, the product of the wavelength and the frequency must be the speed of the wave, or for electromagnetic waves, the speed of light. Strange as it might seem, in some circumstances the behavior of light can be explained more easily understanding light as composed of particles called photons. Even though the characteristics of particles do not seem to be related to waves, many experiments support the particle nature of light, and that approach is widely useful in the development of technology. One key property of photons is that each of these particles carries a specific amount of energy that is related to the frequency of the wave model. The radiative energy carried by a photon of light is the product of the frequency of the corresponding wave multiplied by the Planck's constant. From this relation, we see that higher frequency waves are associated with more energetic photons. Since the frequency is related to the wavelength, the energy can be calculated as well as the speed of light divided by the wavelength multiplied by Planck's constant. Thus, longer wavelengths correspond to lower energy photons. Waves or particles, we are fortunate our eyes and brain coordinate to detect light and to interpret its properties as a rich variety of brightness and colors.